Okay, so we have finished talking about stars, but we have not finished talking about all the stars. We are going to focus today on a star that is very special to each and every one of us.
Oh, it's me.
So there goes our ship. And if we back up after turning on the warp drive, here we go, and, well, it's about time.
How long did that take?
Oh, it just took about 3 seconds, I'd say. So now that we're done with the regular solar system, we are going to now go a little bit closer to the sun than we were when we were next to Mercury and examine it more closely. The sun is what we'll be talking about today. Do not stare directly into it for too long.
Yeah, the people on other planets? Yeah. The Martians?
Yeah, what do you think Martians call the sun?
I don't know. That's a good question.
Maybe they call it
They could. So go ahead and write down this information here. We get the word sun from the Old English word sunni, and that word referred to the sun. They really spent a lot of time making their letters back in the day, I think. Yep.
So we need to know the rise part.
Yep. Yeah, and actually, I don't think they recycle things in the classrooms, so it doesn't matter which garbage you put it in. Unfortunately. So in terms of history, this was kind of a big deal way back in Egyptian times. Write down this first bullet point along with that hash. And then after the first bullet point, also do the second one. You can cut it off right here. So Pharaoh Akhenaten chose to worship the sun, and the sun is known as Aten. So you got to make sure you know the difference between those two things. Ra is the Egyptian god that's associated with the sun. Aten is the sun itself.
Can we watch the Indiana Jones episode where they use the sun to open up the channels?
We should do that. Maybe near the end of the semester.
I called it an episode? Oh, man. Well, there's like 7 of them. There's like 4. Which one is that?
I ain't never watched Indiana Jones.
Really? Dude, I had all Star Wars movies. Okay, so we need the first one.
Yeah, everything up until this blue.
How do you say that?
This one here?
Yeah.
I think it's Akhenaten,
I saw that on one.
but I could be horribly wrong. I don't know. So yeah, that was a big deal in Egyptian history, where they chose to worship the sun itself instead of the god associated with the sun. Make sure you know the difference between those two things. The sun is much larger than any of the planets that we've dealt with up to this point. The diameter is 865,000 miles, almost a full 1,000,000 miles in diameter. That's much larger than anything we've seen so far. I think Jupiter was 69,000 miles or something, so it's much larger than Jupiter. Distance to the Earth is 93 million miles, or 1 astronomical unit. That's where that unit comes from. In terms of volume, you could fit over 1,000,000 Earths inside the sun. Yeah. Here's a little size comparison. You got the sun right here, and there's adorable Jupiter. And if you go further down, you can just barely see the Earth and the other planets. The sun is massive compared with all those things. From this slide, you can write this whole thing down. How many Owens? That would, yeah, we could figure that out, I'm sure.
You'd have to figure out Owens, like,
Yeah, we would somehow. We'd have to curl them up into a cannonball and just, we could do area and volume measurement with that. We just got to figure out the average Owen radius.
Hey, what's the other stuff? What's the other stuff?
Wait, would it be a number? Like, would it be a real
2%?
Um,
No, it's 2% Owen.
Yeah, 2% Owen.
Wait, other stuff. Do we know what the other stuff is?
We do. I don't remember off the top of my head. So I'd just be guessing. Probably like candy bars or something.
It's amazing. So,
Yeah, write the whole thing.
my partner's gone, man. I don't want to Owen. It's easy everyone else. See, English not bad for me.
So yeah, keep it down a little bit, folks. When we're talking about the sun here, then what it's actually made up is plasma. That's what makes up the sun. And when we say super hot ionized gas, ionized just means it has a charge. And so when we define plasma, that's one of the main things. It's not just super hot particles, super hot atoms or molecules. They have to have a charge to them. And those charges play a big part into the solar wind that we'll eventually talk about later here. So, a little bit about the sun's core. Go ahead and write down the first bullet point. Yep. Just the first bullet point. Depends on exactly where you are on the surface of the sun. It changes.
Is there like a sun for the sun?
Not really, because
Like,
the closest...
does the sun rotate around a different sun?
Kind of. I mean, that's a really good question. The sun and the entire solar system actually rotates around the middle of the Milky Way galaxy. So, yeah, we're all kind of going around a circle within a circle.
But then there's another circle outside that, isn't there?
Yeah, the Milky Way is kind of moving with respect to other galaxies.
Does the sun have its own orbit, like spins on an axis?
Yes. Yep.
So we need to find the center of space.
It's Earth. Everyone knows the center of the universe is Earth.
You know, there's actually a fair amount of research that kind of points in that direction that we'll get into later. If you look at a map of all of the galaxies that we've ever found, they create like a circular pattern around where we are.
It's just a giant arrow.
It's
I don't know.
right.
Is space a circle or is space a rectangle? Or square?
Well, it's just
Space is there.
it's everything. It's all out in
It's
every
like-
direction.
What would a picture of infinite darkness
Darkness
be?
means
Well, it would be real dark, I guess. Infinite. I mean, it all depends on.
I don't think so.
We do talk about eventually how the universe is shaped, and that's something we talk about when we get to like black holes, because they impact the shape of different parts of the universe.
Space.
So yeah, you're gonna what in space?
I'm not gonna end space. I'm gonna poke through and find heaven, just like the 1, 2, 3.
Right.
That's actually kind of a cool.
That is a neat way of looking at it, isn't it?
That's cool.
All right. So a little bit about the sun's core. The reason the sun is so hot and the reason it gives off so much light is because there are nuclear reactions going on every single second in the very middle of it. What you have is you've got hydrogen atoms combining to create helium atoms. And so that is known as fusion. You're fusing those two hydrogens together to get helium. And the result of that, a byproduct of it, is radiation, and a byproduct of it is just explosions going out every second in every direction. That's what actually gives the sun its shape. And it's only possible because of the core's extremely high temperature. If you don't have that high temperature, and if you don't have the massive amount of pressures that are present in there, you're not going to have this occurring. But those are the conditions in the middle of the sun, and that's why that occurs. This nuclear fusion releases gamma rays outward in all directions. These can be very, very harmful if you're too close. And that's something that we have to concern ourselves with if we're going to get closer to the sun with humans or something like that. So these are the different zones of the sun. We just got done talking about the core. The next zone we're going to discuss is the radiative zone. So go ahead and for this zone, write down just the middle bullet point. Energy only moves outward. The middle bullet point. Right there.
So I looked up composition of the sun
Sure.
and it took me to NASA and it said opportunity for life and it said, well, the sun isn't a great place for things to live. And I was like, oh, really? Are you going to talk about does anything actually live there?
No, nothing lives there. It's way too hot. We'll get to some actual temperatures in a little while here, and you'll see exactly how impossible it would be to live there.
I'm going to make it possible.
You give it your best try. So as you can imagine, in this radiative zone, if in the core we've got all these nuclear reactions happening every split second, all that energy is going outward. And so this radiative zone is just a zone where you've got all this energy. Keep it down a little bit, folks. All this energy is constantly going outward towards the edge of the sun. That's what's going on in the radiative zone. That's all you need to know there. Next, we've got the convective zone. From the convective zone, go ahead and write down these middle two bullet points. The hot gas rises, cooling as it does so. Once the gas cools enough, it sinks back down. So you guys know how warm air on Earth rises, right?
Yeah.
Yeah. The same thing's true on the sun. The further, well, all of this stuff in the radiative zone is super, super hot, and it continues to move outward. And what ends up happening then is eventually it gets to a point where it cools because it's far enough away from the core that this gas starts to cool down. And as it starts to cool down, it starts to fall down. And as it gets closer and closer again to the radiative zone, it heats up again. And because it heats up, it rises, just like warm air rises. And so that's why we call it the convective zone, because it acts just like air does on Earth for convection. Warm air rises, cold air descends. The same is true with the gases on the sun.
So it's like an infinite. So is it like an infinite heated ball?
Basically, yeah.
Well, so it won't ever stop.
You mean the convective zone or the sun itself?
Yeah, like can it like run on a gas?
Eventually it will.
Oh, really?
And that's what we'll get to. We'll get to that later on, what happens when stars die.
But I'm just trying to think, how cool is cool?
We'll find out soon. We'll compare the actual temperatures shortly. Go ahead and write this down. When you actually look at the sun, you're looking at the photosphere. You should know that region.
So right now, right?
Yep.
You're trying to tell me that's not the surface of the sun.
Well, looks like I got to eliminate one of these ofs, huh? That's probably been that way for 10 years. There we go. So when you actually see the sun during a sunset and you're looking at it, what you're looking at is its quote-unquote surface. You wouldn't actually be able to walk on it because it is still a big ball of gas, but that's the part of it that you're actually seeing when you do look at it. So when you see the sun right here, you're seeing the photosphere. Another part of the sun, what's it? Another part of the sun is called the chromosphere. Write down chromosphere and that it's the sun's lower atmosphere. So this would be above the photosphere. Well, you're kind of looking through it. It's kind of like if you look at Earth, you're looking through our atmosphere to the surface. Same thing's true here.
So the sun isn't solid or liquid at all. Like if you
No,
fire.
it's all gas. Yep, plasma.
Really, I always thought like it would be like ooh. Like,
You
I
know,
always thought it was like lava.
It's weird because when you get to temperatures that high, it's hard to say something is a solid or a liquid because it all behaves kind of differently from each other. It's definitely not a solid, but it kind of looks like a liquid if you really zoom in on it. Yeah.
You think about your, like, if you, like, let's, like, touch something, like, what would happen? Like, your finger melt or just, like, disintegrate? Just,
Like something sun temperature,
yeah.
it would vaporize instantly. Yep. Because, like, heat is just friction. It's molecules going really, really fast, and you feel that as heat. So the molecules are moving so fast here, it would like be putting your hand to a molecular buzzsaw. It would just take all the molecules and atoms and just gone. Vaporized. Even if it was like, oh, there's the sun. You'd be like, oh, half my hand. So if we were to actually look at the sun's chromosphere, it would look like this. Looks kind of ugly, kind of like the surface of Venus. But that's not what we actually see. This is taken with a filter. The only way you can see the chromosphere of the sun is if you're looking at it during a solar eclipse, like the one that happened 3 years ago, or the one that's going to happen 4 years from now. And this is the edge of the chromosphere here. You can see it just peeking out.
Did you take that picture?
No, I did not. It kind of does, yeah.
This really.
Do corona. It's the sun's outer atmosphere. Just the top one. The corona is the sun's outer atmosphere. And just like the chromosphere, the sun's corona is only visible during a solar eclipse. Here's what it looks like. Yeah, it's these lines, and you can see sort of the chromosphere coming out right about like this, and a little bit here and over here. It's just the outer atmosphere of the sun. It extends quite a ways. All right, you guys ready for some temperatures here?
Yeah.
So we've got different parts of the sun. We've got the photosphere, the chromosphere, the corona, and the core. Anybody want to make a guess as to how hot any of these places are?
15 degrees Kelvin.
And which one of those would that be?
The
The corona?
I think that's the cold.
Okay, so maybe the corona is the coldest. That would make sense. It's the furthest away. How hot do you think it gets in the core?
22 degrees Kelvin.
Incorrect.
I close.
22 degrees Kelvin is like almost absolute zero.
Oh, wait.
You meant 220.
What's
220? Okay, so you're almost to the boiling.
I think it's about
Okay, in my mind, I thought we went to 23 to negative.
What would a million degrees Celsius be?
It's a good question. I don't know. So maybe in the millions? In Fahrenheit or Celsius? For the core?
27 million. 27 million.
What about the surface? How hot do you think the surface is?
300,000.
300,000? So we've kind of got millions of degrees for the core, hundreds of thousands for the surface. Let's find out.
The core is 27 million.
Oh!
Yes,
you're right.
Here we go.
27 million.
The core is a blistering 25 million degrees Fahrenheit.
It was about, it says about 27
Where's the
million.
surface?
The photosphere
Oh.
is only 10,000 degrees Fahrenheit.
Only?
I know.
That's not Kelvin, is that?
Only?
That's
Wait.
like,
Isn't the photosphere closer than the corona?
Yeah, it sure is. Go ahead and write down that the core is the hottest area. That's all you need to know from this slide.
I want to write the.
How does one measure that? Like, how do they know that?
They,
Just say that the core thought.
I mean, I'm thinking they must just drop some. Well, for the core, they must just make some calculations based on the size of the sun and the energy it's putting out. In terms of the corona, they've probably actually sent direct measurements into the corona and the chromosphere. I don't think anything would survive to the photosphere. I don't know how they'd calculate that.
You know those guns that they gave us when we walked to school?
What?
That work?
Oh, the ones that they... I thought you said the guns that they give you when you
Yeah,
come to
that's
school.
what you said. You did.
I did.
That sounded really bad.
But like, you think that would work?
Shooting it with a gun? Oh, with the temperature measurement.
Oh! I didn't get that.
To an extent, that would work if you got close enough. You'd have to get pretty close, though.
You know how hot the spaceships can handle? Or satellites?
112 degrees Kelvin.
I think it probably depends on how long they stay that close. It would probably be somewhere,
We bend
I'm
it?
kind of just guessing. I'd say maybe 5,000 degrees is as hot as they could take.
Oh, I say
for-
if we bend it, the photosphere.
No, we haven't been to the photosphere. Because you can see the corona is super hot, so we'd never survive the corona. Now, the reason for these temperature differences here is because, listen up, folks. The reason the corona is actually so much hotter than the photosphere is because as the sun is giving off its plasma, it travels outward. And because the sun has such a strong magnetic field, the magnetic field actually traps a lot of this hot escaping plasma. And so that's why it's actually hotter out here than on the surface. That plasma on the photosphere is always going outward, but it's actually trapped and held in these positions by the magnetic field of the sun in the corona. So it's kind of a strange phenomenon.
So it's kind of like Earth. It's like we have our atmosphere and it keeps us warm on the inside. Like,
Yeah, because as you get beyond the Earth's atmosphere, then that sunlight is not filtered, so it actually does get warmer if you get above, certain areas, because then the atmosphere isn't stopping that heat from reaching us. That's why the moon, it can be 200 degrees Fahrenheit, negative 200 degrees, because there's no atmosphere to stop some of that heat from coming in. So yeah, that's another good way of describing it. Exactly. And this is a more colorful way to describe the sun's surfaces. It's like a gobstopper almost. Okay. So the sun is just made up of superhot gas, so the question might be, why doesn't all of that gravity that the sun has just cause it all to condense into a very small area? Because the sun has a massive amount of material. If you could actually put a solid surface on the sun's surface where the photosphere is and be able to walk around on it, you'd be crushed because you'd weigh so much. There's lots and lots of gravity there. Any guesses as to why the sun doesn't collapse in on itself? Yeah. Yeah, that's exactly right. So the reason that the sun doesn't collapse in on itself is because on the inside, you've got those nuclear reactions occurring. You've got that nuclear fusion going on, which causes massive explosions pretty much continually throughout as the sun goes, from one second to another. So that's all going outwards. Meanwhile, you've got gravity trying to pull it in, and what ends up happening is you get something known as hydrostatic equilibrium, a point at which those forces equalize. And that's why the sun is shaped the way it is. You've got all of that force coming out from the nuclear reactions, and you've got all the gravity pulling in because of all the mass. When they equalize, you've got that equilibrium. Question?
Was there ever, 1 second that there wasn't a explosion, the sun would just disappear? Or did it become a lot smaller?
If it's just 1 second, then it would collapse a little ways. That's not long enough for it to completely collapse.
5 seconds?
Maybe.
would it turn to a black hole then?
We'll get to that. I don't want to jump into that into that part of the forest just yet, but we will be getting there. That's a good question, and we will address that. Here's another way of describing it: gravity in equals pressure out. Yeah, Pac-Man maybe has some acne there. Some. What's that? Ouch! Yeah, well, that's a dark way of looking at it. I was gonna say Pac-knee instead of Pac-Man. Pac-knee. So yeah, go ahead and write down this slide. Yeah, this is a longer one.
This is the last one?
No, I think we can keep going a bit longer.
No,
Well, we'll have probably 1 or 2 more slides to write down, is my guess. We're not going to be finishing the sun today. We're going to carry this through tomorrow.
Oh, okay.
Yes. Sure.
was so upset.
Let's say the sun disappeared. How long can we survive?
It's a really good question. We'd actually be able to survive for, I'd probably say, several months, because
Once all water sources freeze.
well, that's the thing, yeah, because we do have an atmosphere, so that's going to keep a lot of the heat in, but it will escape over a period of weeks and months, and eventually you get to a point where you can't grow food anymore, and water all freezes, and then you'd pretty much be screwed after that. What's that?
Oh, yeah, absolutely. It would be so weird. It would be dark all the time.
Right.
You know how complete chaos that would be though?
Oh, yeah, that would be nuts.
Everyone
I
would
watched like a video on
Yeah?
I'd be ready for a long time.
because it said we could live for like about 2 months. But
Okay.
it would screw up everything. It screw up your sleep schedule. It would screw up the nocturnal animals. The nocturnal animals would basically just be out all the time.
Right.
And it would screw up everything because then you would lose all your plants. You would lose oxygen from the trees. And you would lose the water sources.
Yeah,
You'd have to find like some way to get water.
it's amazing how everything on Earth is dependent on the sun being consistently warm and consistently bright and doing exactly what it needs to do. That's one of the miracles of our whole solar system. And one thing that you'll see later on, too, is our sun is very, very stable. Most stars that we see with exoplanets going around them are very violent. And they send out flares that just engulf these worlds and make them uninhabitable. Our sun is just perfect for life. And it's something that we take for granted. Yeah, we are, kind of. We'll get to those. So, in terms of this, you know, life supposedly evolved billions of years ago. The first life did. And, you know, if that's true and that time scale is true, then the sun would have been much younger. And if it was much younger, it would have been smaller and given off less heat and given off less light. So if you wind the clock back that far, the sun would be actually so dim and so, you know, much cooler that the Earth would have been completely frozen when life first evolved. And obviously that's not the sort of thing that could happen. They call that the faint young sun paradox. And it's a big problem for the naturalistic worldview. The solar wind is something we need to talk about too. So, you can skip writing this down, but just a little bit about the solar wind here. The sun has all those nuclear reactions going on inside, and if you know anything about the side effects of being near a nuclear explosion, you know that you get radiation poisoning and that it's not a good thing. The same thing is true with the sun. It gives off its own radiation, and it shoots out everywhere in space in all directions. And if you don't have protection from that, you're going to have all sorts of bad things happening inside your body genetically. Because when that radiation hits you, it messes up cells and it messes up the DNA inside cells. And it really can cause lots of issues. If you've ever heard or seen about some of the side effects that survivors from Chernobyl or some of the other nuclear disasters had to endure, it's pretty sad and pretty awful stuff. So it's not the sort of thing that you want to be exposed to. But the sun does give off a lot of radiation, and we call it the solar wind. Solar wind is kind of, it sounds almost like a warm breeze, but it's anything other than that. It is very harmful, and if you're not protected from it, you're going to die. And the way that we're protected from it on Earth is we have a magnetic field. And our magnetic field deflects all of that radiation around us. And so we're pretty much safe from it. Yes?
So what's the difference between like a solar flare and the solar wind? Is like solar flares words and those are only often made when like a sunstorm.
Sure, yeah. A solar flare is something we'll talk about soon here. Solar flares are a massive eruption of basically the material and the plasma that are on the sun's surface and coming up from underneath. The solar wind is just those radiation particles, and those can be different from the actual material on the sun's surface. But we will talk about solar flares soon. And, you know, solar flares, they do contain that radiation too, but they're just two different types of the same thing.
So when you see like a big ring, kind of like almost like you go through it and then it'll like go back into the sun.
Right. That's called a prominence, and we'll be getting to that too. You guys are big fans of the sun. This is fun.
Well, I think it's seen that video.
Yes, it's just it's kind of
So sunspots is something that we have to dig into a little bit here. And sunspots basically look like acne on the sun. And the reason sunspots occur are because of magnetic fields. Go ahead and, let's see, finish off by writing down that magnetic fields cause sunspots.
So it's basically just the material is like turned into a solid.
Well,
Is it cold enough that it just turns darker?
it's cold enough that it turns darker. And next time when we pick it up here, we'll talk about exactly why it's so much colder in those regions. Sure.
Well, they need a pattern.